How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at solution stoichiometry and titration. So our objectives will be to describe the technique of titration and use it to determine the concentrations of unknown solutions, meaning the concentrations of a solution that's unknown. All right. So what is titration? Let's start there. What's this big new word? Titration is a technique used to determine the concentration of a solute in a solution. So like, for example, we have a solution of HCl. We don't know what its concentration is. Titration can help you figure that out. So it involves combining a sample solution with a reagent solution whose concentration is known. We call this the standard solution. So it's like if we're trying to figure out HCl, we're like, I don't know what the concentration is. Well, then we're going to use one whose concentration we know to react with it. We call that the standard. So the standard is the one we know, standard solution. The solutions will then react once we mix them together. Sometimes we have an indicator if it's needed, like a dye or pH indicator, depending on what we're reacting. That's going to indicate the end point, which is when they've perfectly reacted. Oftentimes it's like an acid-base titration that we're doing, and we use an acid-base indicator that changes color with pH, so we know when the endpoint's reached. And once the endpoint is reached, you can use the amount of the standard solution used to react with the sample solution in order to figure out the concentration. Because, So here's a classic scenario. You have a solution of HCl with an unknown concentration. You'll need to perform a titration to determine its concentration. So things you're going to need is a sample of the HCl. You'll need a standard solution of a base, like sodium hydroxide, whose concentration is known. A pH indicator that will change color. Most of the time in lab, like we'll use phenolphthalein. It has a very apparent color change from transparent and clear to pink. So the endpoint's going to be like right when it starts to get a tiny bit pink. It's going to be almost pH of 7, but it's definitely going to be close enough for what we're doing. And a flask to mix those two things in. You also need the burettes, and they're what are going to hold the HCl. So these burettes are going to be filled with, here's the HCl on one side, and you're trying to figure it out, but you'll also have another burette with like the sodium hydroxide. So the process, basically you keep track of how much acid you put in, whose concentration you don't know, and you keep track of how much of the sodium hydroxide standard solution you added until you reach the endpoint. The endpoint's going to be apparent when you have the phenolphthalein changing from clear to light pink. And then you use this data in the balanced chemical equation to determine the unknown concentration. Right, so let's take a look. Here's a flow chart. What is the concentration of a HCl solution if X amount of it is neutralized by Y amount of some molar NaOH solution? I'm keeping the numbers out of it for now because I want us to think about it. So first you need to start with your balanced chemical equation, because you need to know, well, how much HCl is needed to react with each NaOH. You need to know that ratio. So we're starting with, all right, we know the volume of the acid. We don't know the molarity of the acid, but we do know the molarity and the volume of the base. So how are we going to connect these two? Well, let's think about it this way. If we knew the molarity, then we can get the moles of the acid, right? I'm kind of working backwards here. Once you know the moles of one of those things, you can use the balanced chemical equation to figure out, well, how many moles of the other one would it be? And then you can use, again, the molarity expression to connect the two. So here I go, hey, I know the volume and molarity of my base. I can use the molarity equation to tell me how many moles of my base I used. I can look to the balanced chemical equation to connect how much of the base was used to how much acid must have been there. So now I know my moles of my acid, and I also know the volume of the acid that I used, so I can get the molarity of my acid. Sometimes they may also ask you, like they want to know how many grams are in that solute, or how many grams are in that solution of the solute. And then that's where you'd use the molar mass, right? Converting from moles to grams is something you've done before. Use the molar mass for that. So example problem, what is the concentration of an HCl solution if 20 milliliters of it is neutralized by 12 milliliters of 1 molar NaOH solution? All right, so first you need the balanced chemical equation, so I write it out. It happens to be simply balanced right there, so it's 1 for all those coefficients. And what's our process going to be? If I'm looking at the flow chart, maybe this is how my mind's thinking. I know the volume and the molarity of my base, but I'm trying to figure out the molarity of my acid. So I know I can connect them through this path, right? So I'm going to start with the volume of my acid, or my base. I use 12 milliliters of my base. I'm going to convert that to liters, right? So I times it by 1 liter divided by 1,000 milliliters. So my milliliters cancel out. And I know that my molarity was 1 mole of NaOH per liter of solution. So now my liters cancel out. I'm left with moles of my base, right? So this part here, I got my moles of my base. I've gotten to this point in that flow chart. So now I need to look at my balanced chemical equation and go, how can I relate that to moles of my acid? I go, well, from here, for every 1 mole of my acid, it reacts with 1 mole of the base. So now I've canceled out moles of NaOH, and now I have my moles of my acid left in terms for my units. I go, all right, well, I used 20 milliliters of it, so I got to convert milliliters to liters, which I did right here. And then, so I divide by 20 milliliters, so I end up with moles per liter, and then I get 0.60 molar. Right, so this is the route that I followed. I went from moles and molarity and volume to get moles of base. I looked at my equation to figure out how that connected to the acid. So I got my moles of my acid, and then I determined my molarity because I knew the volume. All right, so one more example. I have 45.5 milliliters of 0.500 molar H2SO4. So that's my acid, right? So this is my molarity. This is my volume. It's used to neutralize 20 milliliters sample of NaOH. So I got my volume on my base over there. What is the concentration? So I'm trying to figure out the molarity of my base. So I'm trying to get to over here. I know my volume and molarity of my acid. So how am I going to get there? Well, I'm going to have to go, all right, well, from the molarity and the volume of my acid, how many moles of the acid do I have? I'm going to use the molarity equation for that. Once I know that, I can look at my balanced chemical equation and go, all right, well, how much base? How many moles of base had to have been there? And once I know my moles of my base, I also know the volume of my base, so I'm able to get my molarity of my base. So let's do that, right? Let's get the moles of my acid first. First, I'm going to do 45.5 milliliters. I got to convert that to liters. So I times that by 1 liter over, double line apparently, over 1,000 milliliters. So now I got the equivalent liters. So now I can times it by my molarity of my acid, which is at 0.500 moles per liter. Liters cancel out. Now I'm left with moles of H2SO4. So that is right here. That's where I've gotten. This whole part is the moles of my acid. So now I got to look at my balanced chemical equation, which some TV movie magic right here. I already did it, right? So I figured out the balanced chemical equation. So now I can look at how many moles of acid react with how many moles of base. All right, well, if I'm trying to cancel out moles of acid, I got to put acid on the bottom because it's on top. So it shows for every 1 mole of the acid, it reacts with 2 moles of the base. So 2 NaOH, and that's 2 moles, right? So moles of H2SO4 cancel out. I'm left with just moles of sodium hydroxide. So I'm right here now. So now I can convert it to molarity. Well, they told me how many milliliters I used, but I need that to be liters. I need to divide by liters. So I know that 1 liter is 1,000 milliliters. And I know that I used 20.0 milliliters. So my milliliters cancel out, and I'm left with my liters. So now the only units that I have left are moles of sodium hydroxide per liter. So now I pick up my calculator and do some number punching. And I get 2.275 moles per liter. And now I'm going to do a little check, right? I'm going to check kind of logically. I used 45 milliliters of my acid and 20 milliliters of my base. Don't worry about that. So yeah, that's what I get. I get 2.275. So to summarize, can you describe the technique of titration and use it to determine the concentrations of unknown solutions? I hope so. Okay, see you in class. Okay, bye.